Okay, so welcome everyone. Welcome to today's lecture on the foundations of quantum mechanics. This is the third in our series. Last time we started discussing Bell's inequalities, and this is really the heart of the lecture series. So I want to state in repetition, I want to state that Bell's inequalities, together with certain experimental results which now exist, tell us that nature is mysterious in a very precisely defined way. And the amazing thing is you do not need the theory of quantum mechanics to derive Bell's inequalities. And you do not need the theory of quantum mechanics to understand that nature is mysterious in this very precisely defined way. And because you do not need the theory of quantum mechanics to understand all this, I thought I start this chapter by going through an explanation or an illustration, let's say, of Bell's inequalities, which does not refer to the theory of quantum mechanics. So for the moment, you may forget anything you know about Schrödinger's equation or operators or quantum states, and you just concentrate on the logic of what we are going to discuss. The setup that I want to discuss is an illustration of Bell's inequalities that was invented by David Mermin in the 80s. And we started discussing the setup last time. So here's the setup that we started discussing last time, where you imagine you walk into a lab, you don't have any preconception of what awaits you. You just see that there are three boxes. There's a box in the middle. It just has a button that you can press. And if you press it, then some kinds of objects or clouds or something you cannot quite make out are emitted to the left and to the right. And then at the either end of the room, there are two boxes that you may label A and B. And these boxes are very peculiar. On these boxes, there is a dial where you can set one of three settings. And then there's always a light, a red light and a green light. And it turns out that once you press the button on the box in the middle, then after a very short time, on each of the boxes A and B, one of the lights flashes. So either the red or the green light. And now you start to investigate things further, and you make a long series of experiments where you choose different settings and observe the colors that are lighting up in each of the experimental runs. And you find two very simple observations that summarize everything that you see. The first one is, whenever the settings are the same, so for example, 3 at A and 3 at B, or 1 at A and 1 at B, whenever the settings are the same at the two boxes, then the same color lights up. So that is always true. It need not be always red, it can also be green, but the color on the left box is equal to the color on the right box in all the cases where the settings are the same. And then secondly, you do another series of experiments where you take the settings completely randomly. So in other words, the combination 1-1 is just as likely as the combination 1-2 or 1-3 or 2-3 and so on. There are 9 combinations, so each of these combinations occurs with 1/9 probability. And if you do choose the settings randomly, and you still observe the colors that light up, then you find that the colors are also uncorrelated in this long series of experiments. In other words, the combination red-red is just as likely as the combination green-green or the combination red-green or green-red, and they all occur with 1/4 probability. So these are the two observations. Same settings give same color, random settings give random colors. The question is, should you worry? This is where we left last time. And just to make it really clear what is emitted to the left and to the right. You can't quite make out. It's as if there is a little cloud and you don't know what's inside. Maybe these are particles, maybe something else. It's not quite clear. But now let's investigate this further. The first thing that you can do in such a situation is just to very carefully observe the statistics. I already gave you the two summary observations, but you could be a bit more detailed in your observations. And you could ask yourself, let me take, say, the setting 1, 1, the combination 1, 1, and let me make a little table that tells me how often does the combination red-green occur, or red-red, and so on. So let's do this. Let's imagine that we have made such a table. So you observe the statistics. And we just imagine a potential outcome of this little experiment. Just an example. Here you make a table. These are the two settings on the left and on the right. And then you might get the outcome red, red. And so the question is, what is the percentage with which you get such an outcome? And I will plot the percentage to the right. It might be 20%, let's say. What is the probability, though, to get red-green in such a case where the settings are the same? Anyone has any idea?
0.
Just put the answer in the chat, 0, exactly. Because we said whenever the settings are the same, then the colors also must be the same. So red-green is simply excluded. Likewise, green-red is excluded. But green-green, again, is one of the possibilities. And since everything has to add up to 100%, probably this is 80%. And then you can go on and make the same little table for the combination 1, 2. And again, you ask, what's the likelihood to get red, red? And you measure something. I don't know what, so let's just put an arbitrary number, let's say 10% or so. Then you would have red, green, and maybe you have 40%. This is just an example. You have green, red, maybe that's 30%. And you have green, green, which then has to add up to 100%. And you could go on and on and on. And for all the 9 combinations of settings, you could make such a table of observed statistics. And these could be quite arbitrary, except of course we have the 2 rules that if the settings are the same, the colors have to be the same. If you average over completely randomly chosen settings, then also the colors appear randomly. So each color combination is 25%. Now, the first thing I want to make clear is that if someone gives you such a rather arbitrary table of statistics, there's a very, very simple way to produce an arbitrary statistics. And this is not very difficult. Let's say you have your 3 boxes with the source in the middle and A and B to the left and to the right. And at A and B, you have your settings. Now, what you could do in principle is, of course, you have in the background some kind of computer, some machine. And you send the settings that you chose to this computer. So you send it the setting at A and the setting at B. And then the computer looks up in this table. You first provided a table of arbitrary probabilities that should be obeyed, looks up in this table and will produce this color combinations with the appropriate probabilities. Since it knows both the settings, it can do so. And then once it has done so, it will send back a signal to each of the stations A and B and tell it what should be the color, what should be the result that should light up. And in this way, you can really produce completely arbitrary statistics, and it's not very difficult. Now, if this works, also many other versions of the same idea would work. For example, you could have something where you even get rid of this extra computer, and maybe all this calculation really takes place inside the box in the middle. Who knows? Yeah, because you don't know anything about the inner workings of these things. And again, the box in the middle could receive both settings and then answer with a suitably randomly chosen color combination that is chosen so as to give the correct statistics. And maybe you don't even need the box in the middle, actually. You could also have a situation where you directly wire up the two boxes, and only one of the boxes sends its setting to the other one, which of course knows its own setting anyway, calculates things properly by looking up in the table, produces a color combination and sends back the color that should light up into the first box. That's another possibility. Or finally, if you make sure to look around the room and you do not discover any such cables, well, of course, we know that we can also do without cables. So we could have a radio signal going between the two boxes. And in all these cases, it would be very, very easy to produce arbitrary statistics. So the only constraint on the statistics would be that things add up properly to 100% as they should. And other than that, there is no constraint. So this is the easiest explanation for what you observe, no matter what exactly the statistics would be. And so in order to make any progress, you try to analyze whether any of this happens in the lab, and you don't see any cables, and you try to do a Faraday cage so as to screen electromagnetic radiation, but even that doesn't change anything. And so after a while, you come to the conclusion, no, it's not any of this. There is no communication between the boxes, at least not in a simple way. So no cables, no radio waves, no light waves, and so on. No electromagnetic radiation. But then again, we know there are other mysterious physical fields and particles. For example, there could be communication via neutrinos, who knows? Or maybe other fields that we haven't discovered yet. And so that's a little bit more tricky to rule out any of this. And in general, you can't. You can't know whether it's not some undiscovered field that provides a communication channel between boxes A and B and tries to produce an arbitrary statistics by some as yet undiscovered mechanism. So the logic would allow all this. However, there's an important idea in this whole game. And the idea is that one can at least try to rule out all communication that does not occur faster than the speed of light or faster than some arbitrary upper cutoff for the speed of information transfer. So you can try, and we will learn in a moment how, to rule out all communications that don't need signals faster than light. And so the question is, how does this work? Well, you somehow have to make use of the fact that things cannot now be infinitely fast. And so the idea is that you would choose the settings just a tiny moment before the light displays the result, red or green. And if this delay between the settings and the result is short enough, then you can make sure that even a light signal, which is very fast, would not be able to transfer the information about the setting to the other station or some station in between. So you want to make sure that the time interval is so short that even a light signal could not reach the other station. We can draw the situation here. There's A, there's B. And let's say delta t would be the time interval between your choice of the setting and when the result shows up. And so if within this time you only travel a distance that is shorter than the total distance between A and B, then B cannot yet have any knowledge about the setting that was chosen at A. And as a consequence, B cannot in any way adjust its results so as to produce the proper statistics that you would like to have. That's the basic idea. So you choose the settings just before the results light up such that not even a light signal can reach the other station. So in other words, as an inequality C delta t, the distance you could travel in order to convey the information should be less than the distance you would have to travel to reach the other station. And then you're safe. Then all of this tricky business with the stations communicating with each other or with a third station that tries to look up in the table and produce the correct result combination based on the setting combination, all of this will no longer work. So then you are safe in this regard. So then there will be no communication. So then the results, the correlations in the results cannot be produced by communication. This is what you have then successfully ruled out, at least not by any communication that is not faster than the speed of light. And this is a very important idea. I already wanted to introduce it here. Is there any question at the moment about this idea? So the importance of this idea is you try to rule out communication as the source of the correlations. Okay. Well, yes, this experiment has been done, maybe not exactly in this version, but we will come later to how the actual experiments look like, and they are very close to what we are discussing here. In this scenario, when do you press the button? Well, that may be quite some time earlier, actually, because who knows, maybe when you press the button, two objects are emitted to the left and to the right. They may not even travel at the speed of light. Maybe they are quite slow, so they even need some time to reach stations A and B. The important thing is, though, that between the choice of the setting and the result, only very little time elapses, so that there is no way information about the setting can reach the other station just in time to influence that result. I have a more fundamental question. Who came up with the two observations? Why should they be assumed to be true? Oh, that's of course a very good question. So I could of course lie to you. I could just make up a gedanken experiment which has nonsensical statistics, and we would then find that the statistics doesn't make sense and we would scratch our heads. But I could just make up anything. I could make up statistics which, if you look into them more closely, actually lead to probabilities that don't add up to 100% or so. I could always make up logically inconsistent stories. So in that regard, you have to believe me that what I'm telling you now, this gedanken experiment, or so to speak, is in fact not really a gedanken experiment, but has in some form that we will discuss later been actually realized in the lab. It's still very useful to discuss it in this form, because then you are not getting confused by any of the details of how it has been implemented in the lab, and you can concentrate on the logic. So that's the idea. But your point is well taken. I could be making up something that doesn't make any sense. How do you know if there was no communication at the time you are pressing? Well, there could be communication going on all the time below light speed. And for example, when I'm pressing, there could still be exchange of information between A and B. But if I choose my setting later, then of course this communication will not help the stations to know what was the setting at the other station. That's the idea. Yeah? So the communication will only help once you have chosen the final setting that determines the result. Only then will it be useful to produce the right outcomes, to produce an arbitrary statistics. What does choosing mean in this context? Well, okay, you guys are asking very good questions. So we will come back to this later, and this is part of the discussion, of course, going on. Here, it's still a very naive notion of choosing. For example, you throw some dice, or you have a big book of random results, but you never reveal them to the other station. So you can be sure that they have not been communicated maybe to the other station. And that's what you do. So there, you must come up with an element of randomness that hopefully is somehow not accessible to the other station. If, of course, you have the opinion that everything is deterministic anyway, that say the coin flip that you try at one of the stations to choose your setting is determined by the precise coordinates of all the particles in the universe that have previously interacted, and therefore might in some mysterious way also correlated with the coin flip at the other station being done by the other observer, then we're a little bit out of luck. When we click the state inside the middle box, could it be possible the state inside collapsed? Well, a collapse of a state is a notion that comes up in quantum mechanics. At the moment, we are not even trying to go into these details. So we are not even asking, is this even an experiment where you need quantum physics, or is this another experiment where maybe classical physics would be sufficient? We're just looking at the observations and trying to make sense of the logic of these observations. And of course, to look ahead, we will come out with the conclusion that these observations are very mysterious indeed, and then we will rewind and we will go through the steps how people came to the prediction that such very weird, seemingly nonsensical statistical results would be expected if you did an experiment in nature. And it's there that quantum mechanics comes into play again, of course. Yes, there's another question, whether I'm saying that one should take into account only the information after the settings. Yes, because the results, the statistics of the results is such that they only depend on what precisely were the settings right before the lights were flashing. And so any previous settings that may have been communicated, because there was a lot of time to communicate those, any previous settings are not really relevant. At the moment, so this discussion had assumed that you could produce the correlations by communication. And on the slide before, I showed you that if indeed you do have communication, it would be very easy to produce arbitrary statistics. But now I'm telling you that in this hypothetical gedanken experiment where you went into the lab, you made sure to ascertain that there is no such communication going on. There were no cables, there was no radio communication. And in order to rule out even more fancy ways of communication, such as neutrinos or other undiscovered fields, you did this little trick of testing whether, even if you change the settings very rapidly so that there is no time for even light signals to travel between the boxes, whether the statistics even then hold, and this is something I still wanted to write down, even then, the old statistics hold. In other words, now you're run out of the explanation that rests on communication, and you have to try to come up with different explanations. There are different ways of trying to explain it. We just wanted to rule out the very simplest of them, which would be communication. If one chooses the setting, it is no more random at this moment, yes? All randomness has been left to the RG lights. Is that right? Yes. So once the settings are fixed, of course, the setting is not random. And when I previously said that you say make a series of experiments where you choose random settings, that just means that well, you had a way of producing these random settings, but once they have been set, of course, they are no longer random. The dial does not continue to fluctuate around or do anything. Then they are fixed and you observe the light. But the light is still seems to be random. Okay, someone else points out that if you want to actually take the statistics and compare them, then of course at some point you have to indeed communicate. So one way of doing these things could be that at first A and B work on their own, take their random settings according to a time schedule. Every second, for example, they choose a setting and then choose another setting and so on. And they note down the string of results. They note red, red, green, green, red, 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 and so on. Each of them keeps at first their notebook separately. And then in the end, they come together and they compare, look, what were the results when we had this combination of settings? Okay. So that was already very good. So let's say at this moment in your lab, in this gedanken experiment, you have ruled out communication as a source of the correlations. So then the question is, what is left? How can there be correlations without communication? And it turns out that's actually not terribly difficult. Just imagine the following setting. I don't claim that this has to be true. It's just one possibility, and then we will generalize it. So here's your source. Let's say if you look into these clouds that seem to be emitted where it was a little bit uncertain what these represent, if you look at them more closely, you'll find, oh, there are objects being emitted. For example, a triangle. And if a triangle is emitted to the left, a triangle is also emitted to the right. And then the next run of the experiment, maybe a circle is emitted to the left and also to the right. And in the next run of the experiment, you might have a smaller circle being emitted to the left and to the right, and then maybe even a square and so on. So the source would emit random objects, but they are correlated in such that the same object will be sent to the left and to the right. And then what the stations could be doing is they just measure properties of these objects. So for example, depending on the setting, 1, 2, or 3, you could measure the shape. So it's a circle or a triangle or a square. You could measure the size, or you could measure the color. Actually, if there are only 2 outcomes, then so red or green, you should have only 2 shapes, 2 sizes, and 2 colors. And so the setting could pick which one of these is measured, And the fact that if you take the same setting and get the same result is very simple to understand, because these are identical objects going to the left and to the right. So if you measure a circle on the left, you will also measure a circle on the right. On the other hand, if you measure the shape on the left and measure a different property like the color on the right, then they need not be correlated in any way, because maybe they are really chosen randomly. Maybe there are equally many circles of one particular color than there are of another particular color. Okay, so this would be a very easy explanation to get these correlations, that the objects that are being emitted are correlated in their properties, and all that we are doing is just to measure these pre-existing correlated properties. So let's write this down in a more general way, because we don't want to claim that this is the only possibility, but there's a whole class of such scenarios, so to speak. So the more general hypothesis we could formulate in the following manner. What our apparatuses do, according to this hypothesis, is that they are measuring properties, we could say pre-existing properties of these objects, and that these properties then are correlated, because they have been correlated already from the start. Even when things get emitted from the source, they were already correlated. In that way, you don't have to communicate, because the correlations are already built in. Okay, so is this at least clear, the game we are playing now? No communication, but pre-existing correlation. Okay, I take it that it's probably clear. And so let's now investigate the consequences of this more general hypothesis, that there are pre-existing correlations. Now, what we could do is, for each individual run, when we click the button once and the source emits these two objects or whatever it is to the left and to the right, for each individual experimental run, we could ask, even before the measurement is being performed, what would be the result given any particular setting? So just to give an example and to make it very concrete, we could ask at this station A, if I now were to do a measurement on this object that is being received by A, and if I were to choose the setting 1, what would I get? And maybe for the particular object that we currently have in the lab flying towards station A, the answer would be, oh, then you would get red. And we could ask likewise, well, but if instead I choose to have the setting 2, what would I get then? And maybe the answer would be, oh, then you get green. And then I could finally ask, well, but if I had chosen the third setting, What would I have gotten then? And maybe the answer again would have been red. So you could make such a little table which would completely characterize the object that is about to be received by station A in terms of its properties, as far as these properties are relevant for the measurement that is being performed. Because there are only these three settings, and for each setting, there can only be red or green. Whether there are other more detailed properties of the object, at this point, you wouldn't care. Does this pre-existing correlation satisfy second observation, is a question someone asks. Then I guess you have to tell me what second observation means. Oh, you mean of our original, I understand. So of our original rules, the first rule was same setting, same color. And the second rule was random settings, random colors. Well, very good question. Let us wait for a moment. At this point, we cannot yet tell. I will tell you in a moment how randomness can be generated. So it's not immediately in conflict. Anyway, so this little table encodes the pre-existing properties of a particular object. And I would say we need this. Why does there need to be, at least conceptually, such a table? Whether we write it down or not, whether we know it or not is another matter. But why would we need such a table? Well, we need this because first, we cannot know in advance which setting will be chosen. So we really have to be able to answer for any possible choice of setting. So in other words, the object has to have properties that could be measured. And regardless which property I want to measure, so which setting I choose, it should work out. It should give an answer, so to speak, if you consider the result an answer to a measurement. Okay. Now, you also see one peculiar characteristic of this little table that I drew. We have drawn tables like this before, right? A few minutes ago. But there we always had combinations of settings, and then we had combinations of colors. Here it looks different. Here it looks like I have a table for A, and there would be likewise a similar table for the object being received at station B. And to each of the three settings, I get one of the two possible colors. So in other words, instead of having anything depending on combinations of settings, I really have separate tables for the both sides. So I call this a little table, or you could call it an instruction set. And we have separate tables for both sides. And again, why is that? Why can't we have a table that lists, well, if the combination is 2, 3, then you should answer GR, for example. Why are such tables that list combinations not allowed? So we have no dependence on combinations. Why are such combinations not allowed? Well, simply because we already figured out that there cannot be any signals between the two sides. We set this up and we tested it, and we didn't find any signals, at least not signals that cannot travel faster than light. And so we already know in advance things cannot depend on the combination, simply because none of the two stations and none of the two objects being received by the stations can know what is the combination of settings. So this is why this table doesn't list combinations and only individual settings and individual colors. On the other hand, I said a similar table should be set up for the object that is flying towards station B. And I now claim that actually it has to be exactly the same table. And again, we can explain this. This is now a direct consequence of observation 1 that we started with. So we said when it's the same setting, you should get the same color. In other words, if these tables would be different, even in only one of the 3 slots, then we would have a contradiction. Because then, for example, if they're both different in slot number 3, if I get a red at A and a green at B, then if you happen to choose 3, and you happen to have this object flying towards the station A and station B, then you would get a contradiction. You would have the same setting, but have different colors. That was not allowed. Okay, so this is how we get the perfect correlations in this language of these little property tables. And the question is then, where does the randomness come in? Because in this table, we cannot have any randomness. Why? Because again, otherwise we wouldn't get these perfect correlations. If we allowed for some randomness, for example, in one of these entries, it would say, oh, 90% red, but 10% green, then automatically, because it's fluctuating, it's no longer perfect, you would not get these perfect correlations, same setting, same color on the 2 sides. So the question is, if there is no randomness in the tables, where does the randomness come in? Because there is some sort of randomness observed in the statistics that we see. And the natural explanation would be that even though an individual table, there is no randomness. So for an individual object, if you take setting number 2, you will definitely get green. You can still have random objects, such as we explained just previously with the different shapes and sizes of the objects. So it's random tables, but no randomness within each table. That's the idea. So randomly chosen tables, or in more concrete language, randomly chosen objects, but it's always the same object to the left and to the right. And the object doesn't have stochastic properties that fluctuate, but the properties are then deterministic. So that's the idea. So now I'm ready to answer more questions. So it's like you get an outcome. Sorry, I have to go through all the questions. How can one be sure that the settings are completely random? They might seem random, but could in reality be pseudo-random? That again is a very good question that comes back to what we said before. In principle, maybe at least if you adopt classical view of the world, you might say, well, everything is deterministic. So even my dice or my coin that I flip in principle obeys deterministic equations of motion. So if I were to know with arbitrary precision my initial conditions, that is in principle not a true random process. And the question is then whether that matters. Yeah. So again, this discussion is now going far ahead, coming to material we will cover later. But that's, of course, a discussion that goes on. Now, for this discussion to be practically relevant, it would be best if someone came up with a very crazy model where the fact that the randomness is maybe only pseudo-random really matters and can make sure that suddenly, magically, it becomes possible to get these correlations. And that has not really been achieved. So then the next question. So it's like you get an outcome by writing a code. You already know the outcome now, so you understand what would have been the input, right? I would not. So I fear I don't quite understand this question. When you say writing a code, you mean it looks like a little translation table. So the 1 gets mapped to R, the 2 gets mapped to G, and so on. Is that how you mean the code? Okay, so maybe we defer this question a little bit. Oopsie. Yeah, so sorry. When I say no randomness, I mean no randomness in outcomes for given settings. Yeah. There's another question. So different objects in our little example before, squares, circles, etc., correspond to different tables. Yes, that would be true. I still fear I don't probably understand the question about the code and the knowing the outcome and understanding what's the input. Maybe I first answer another question. How can the table be unique? Well, I don't claim it as, I don't know, unique could be interpreted in that different objects must by necessity have different tables, but maybe they don't. Maybe for the purposes of these measurements, two objects that when looked upon in detail would look to us quite a bit different, they might still have the same table because these are only 3 different properties that we are measuring and the outcome is always binary. So maybe with respect to these very rough measurements, they still agree and have the same table. So I don't mean that tables are unique, but certainly I do mean that tables are deterministic in the sense that for number 2, setting number 2, you get green 100%. You cannot say, oh, I get green 70% and 30% red, because that would immediately break the perfect correlations if you think it through. Okay. So we said that we can get correlations without communication. And if we do so, then we should be able, at least in our head, to imagine that what we are measuring are pre-existing properties of these objects, and it was these properties that were correlated. And then when we're measuring them, also the outcomes will be correlated naturally. If that is so, then even before the measurement, we should be able to draw such a table telling us what would happen if we choose any of the 3 settings, what would happen for this particular object. Then the tables have to be the same at both sides, because otherwise you never get the perfect correlations. We also know that the table itself cannot contain any randomness, again, because otherwise you don't get perfect correlations. But in order still to get some randomness, these tables actually are chosen at random. So that's the current state of the most reasonable model we have been able to come up with. And now, of course, comes the big disappointment, because we will now go and try to figure out a few further consequences of this seemingly very wide class of models. In fact, I want to say, if you don't allow for communication in order to produce the correlations, then as far as I know, this is the only common sense class of models that I could even come up with. If you have now or later, when you think about it, any other possibility, if communication is excluded, any other possibility to produce these correlations in the statistics, then please tell me. That would be very important. Okay, but for now, we stick with this hypothesis, which is very broad. There's still a lot of freedom for us to decide things. And now we come back to our initial observations. We look at the statistics a little bit more closely. And these arguments will not be very complicated now. It's just a few lines. But the consequence will be far-reaching. So let us look at the possible tables that there could be. And there are not so many. You can count them. I mean, for each of the three settings, you have two choices. So it's 2 times 2 times 2 is 8 possible tables. We can say the following. So what is the statistics based on any such model? Well, we can formulate everything now in terms of these tables. That's why they are so useful. So if I have a table where all the settings give the same color, so not only are the colors the same if you have the same setting at both stations, that's clear anyway, but even at a given station, you can pick any setting, you get the same color. So either red or green for all the settings. Well, that would mean if I now look at the combinations of colors that I get at the two stations, I can never get RG or GR, not even if I choose different settings, because say in the first case, it's always R, regardless what you choose. Even if you choose a combination 2, 3 at the stations A and B, you still get RR because there is only R. Okay, so that is quite trivial. But of course, that is not any cause for concern, because the fact that we do observe RG and GR when we choose random settings, that can still be easily explained, at least qualitatively, by saying that, of course, there are many different tables that do not have purely the same color. So we now have to investigate those tables. So 1, 2, 3, RRG, that's one of those. And there are many, there are, of course, many, many more. GRG is another possibility, and so on. So all of these tables, obviously, they have 2 colors of one sort and 1 color of the other sort. It cannot be otherwise. You just have 3 slots and there are only 2 colors, so it's always of the type 2 color of one sort, 1 color of the other sort. So now you can ask, if I have only objects of this type, only tables of this type coming out of my source, and I choose my settings randomly, because this was one of the experiments we wanted to do. If I choose my settings randomly, what will be the outcome? So random settings again means 1, 1, and 1, 2, 2, 3, and all these 9 combinations are equally likely. Okay. So what's the probability then to get RG, let's say? And let's do it to make it concrete, let's do it for this first table, but the same calculation actually applies to all of these tables of this sort. So if I choose randomly the setting at the station A, which remember, I always write first, so this is A and this is B. So if I choose randomly the setting at A, out of these 3 settings, 2 will result in R. So the probability to get an R is just 2 over 3, 2 out of 3. And then at the second station, at station B, again, if I choose settings randomly, the likelihood to hit on the G is just 1/3, because it's just one out of the 3 settings that I could choose that will result in G. And since the settings are chosen independently, I can just multiply these 2 probabilities. So the probability to get the particular combination red-green is just 2/3 times 1/3, which is 2/9. Well, that's simple algebra. And now I claim the following. 2/9 is obviously less than 2/8, simply because I have now reduced the denominator. And 2/8 is 1/4. Okay. So that's great. That's simple algebra. The question is, what does it tell us? Well, the problem is now, we have now covered all the possible tables. There is only these 2 types. Either all colors are the same, or it's 2 colors of one sort and 1 color of the other sort. If both colors are the same and we choose settings randomly, we never get different colors. We never get RG or GR. So the likelihood of getting that is simply 0. If, however, we have these other kinds of tables, well, we do sometimes get something like RG, but still at a probability less than 1/4. And so now you suddenly see a problem. Regardless of the way we pick our different tables or pick our different objects to come out of the source, we never achieve a probability for an observation like RG to be equal to 1/4, because either it's 0 or it's less than 1/4. There's no other possibilities. So this is a very big problem, because remember, when the settings were random, the observation stated that also the color combinations came out random. In other words, every color combination came out to be 1/4. So we will never be able to achieve this, regardless of how we choose our objects, which tables are being observed, because either we are still less than 1/4, namely 2/9, or when the tables are of this sort and we choose the settings randomly, we precisely get 0. So this contradicts observation number 2. And that's pretty bad, yeah? Because we didn't make any very detailed assumptions. We only said there are some pre-existing properties. We were restrained a little bit in order to produce the perfect correlations when you have the same settings. So in a sense, you could say the attempt to get these perfect correlations when the same settings are applied has enforced too much of a tendency towards the same colors, because you see, even if the settings are then chosen randomly, the RG or GR, same calculation, is suppressed, and the RR and GG combinations are still too high of a probability. So we could say observation number 1 has enforced too much of a tendency towards the same colors. And so at this point, I think we should all pause for a moment and underline this result. Because we have done something very, very reasonable. We have first checked that we don't have communication because we understood that if there were communication, we could produce any kind of statistics. So I now claim in this gedanken experiment, in the story, which however will later be verified in the lab, I claim that we have ruled out the possibility of communication. Then we came up with the very simple idea that, well, correlations can also be produced in another way, simply because there are pre-existing correlations and you're just measuring them. And if you do so, then you should be able to say, well, if I were to measure this setting, what would be the result? And then with a few short logical steps and very trivial algebra, actually we arrive at a contradiction. So that's pretty bad. Now, there are questions already. Probability models are considered to be good when the probability, theoretical values, are numerically close to the so-called relative frequency. Yeah, P of Rg determined from theory should be close to number of Rg observed divided by the number of trials. That can actually be determined from experiment. The question is, isn't it our human limitation to fit models to reality? Okay, so that's a little bit hard to answer. Are you basically questioning whether there's a hidden assumption in probability theory? I mean, I guess when I'm okay, so there's at least one statement I can make. When such experiments are done, of course, it is important to then really have sufficient statistics to make sure that the frequencies of the observed frequency of events converges to some value, and then you take this to be the probability. But beyond that, it's a little bit hard for me to follow. Maybe I try to first answer different questions. This table is based on one type of object being observed in one run. Fine. What if the source gives different types of objects every run? But okay, I guess this was what I had in mind. So one run is just emitting one object to the left and one object to the right and measuring these the properties of these objects. So that's what I mean by one run. And then I really mean that probably the source emits different objects in the next run, because otherwise we couldn't explain the randomness that is observed in the results. And these objects may be very different, and as I explained, it need not be that I only have, say, 8 different types of objects or some combination of those, simply because there are only 8 different outcomes or 8 different tables that you could write. Because each object could have also many, many additional properties that we're not actually measuring. And so maybe we never get the same identical object twice in the long series of experiments. But since there are only a finite number of tables, so to speak, that talk about the properties that are important for our particular measurement, since there are only 8 different tables, then I would still assume that if you wait long enough, you get all of these 8 tables, maybe with different probabilities. Maybe sometimes for one of those, the probability will be 0. But if you measure long enough, you will get them at a certain frequency. So I do think that we do have different types of objects, or different objects in every run. It's just identical objects going to the left and to the right in every run. So then there was another question: what if there is another underlying field that propagates at a speed larger than light, to which A and B can couple, from which classical or relativistic communication emerges? Well, if we have something at speed larger than light, then of course all bets are off. Then we have to go back to the initial setting where we do have communication, and then in principle the results could be explained by communication, then of course it would be a challenge to make a physically reasonable model of this, yeah? Because the fact that logically now things are allowed doesn't mean that in reality they will be like this. In reality, we don't expect there to be a little computer somewhere that gets the superluminal signal and then spits out just the right results in order to get the statistics right. So you would then the challenge is different. Then the challenge is no longer that the outcomes are completely by logic unexplainable. Then the challenge would be more to find a physically plausible model that you can look at. Okay, so let's go on with the questions. So basically our models do not work because observation 1 impedes the results to be random. Yeah, you could probably say this, although it's a little bit a matter of taste. We just started from observation 1 because it's a simpler observation, and then we built our model such that we already get the perfect correlations, and then we found it to be in contradiction with the random settings, random colors observation. We could also have started from the random settings, random colors observation that may be a little bit more complicated to implement, and then we would have arrived at a contradiction with the first observation. So it's a little bit a matter of taste. But in the end, there is simply no self-consistent way to fulfill both observations at the same time. That's the important point. Right, so this basically tells us we cannot achieve both these perfect correlations and the complete independency at the same time. Just like we generate random numbers, we can generate random source input here. So far we have assumed we get different tables, and we just know that it was all random settings and random input. Well, yeah, so we would assume that the source probably emits randomly different types of objects. That's what we assume. And when I say something about random settings, this is our choice. This was just, I mean, we don't need to do this. I could also have prescribed to you the detailed probability tables for all the 9 possible combinations of settings. I could have listed the 4 different color combinations and their probabilities. So then that would have been much more information to work with. And then we would still, of course, have arrived at a contradiction. These 2 observations are just the minimum statistical observations that you need to construct a contradiction. And at this point, of course, as I said before, you cannot know whether I'm lying to you. I could just have made this up. I can easily make up a logically impossible scenario, and then you have to scratch your head and come to the conclusion that it's logically impossible. I just have to promise at this point that this is not invented in this way, because there are actually physical experiments that have actually been performed that in some way or another exactly map to this gedanken experiment. Okay. So it's pretty bad, the situation, because it seems that the only reasonable way without communication to guarantee the perfect correlations is incompatible with the other observation. So the question now is there a way out of this? Is there a way out of this? Sorry. Is there a way out of this? We can ask ourselves. Well, the first question was already asked by you. Maybe there is no such experiment. And my answer was, oh, yes, there is. Okay. And the other way out seems to be to go back, as you also said, to the communication scenario and say, maybe there is superluminal signaling. Because if that were the case, you could just have joint instruction sets. So instead of just saying what happens at one of the stations when you choose one of 3 settings, you could make much larger tables that would actually include all the 9 combinations and then tell us, oh yeah, if it's 1-1, you have to give 3 red. If you have 1-2, you have to give green red, for example, and so on and so on. So there would be 9 such entries in the table. And then, of course, again, everything is possible, but that we already knew. So if you have communication, you can do anything. Okay. So this is the situation. And deliberately in this gedanken experiment, no reference was made to quantum mechanics. We did not once talk about the wave function, about anything having to do with quantum mechanics. We just presented the statistics of a seemingly reasonable experiment. We ruled out, we claimed that it has been ruled out that there is communication. And then we found that we can no longer explain the correlations properly within a very wide class of models. And frankly, I don't know any more models that you could come up with in this scenario. So this is where things stand at the moment. And we have now already discussed many of the questions that will arise in the following. But now it's time, I think, to go back and start at the beginning. So where, of course, people didn't come up with experiments that revealed such funny correlations just out of thin air, but they did actually start from thinking about the foundations of quantum physics, and then it developed from there. And so that's where I want to start now. So we will now discuss the earliest precursor of these types of experiments, and that is the famous paper by Einstein-Podolsky and Rosen. Okay, first there's another question. Should we question our assumption that there should be a table for A? Well, very good, very good. So at this moment, of course, it's very hard to say. I mean, when we say there is a table, that doesn't mean that the object comes attached with a table. It just means that, at least in principle, even before the measurement is performed, we can think of what would be the result if we were to perform the measurement according to setting 1, and what would be the result if we did perform the other measurement 2, or what would be the result if we did perform measurement 3. Because this object has some predefined properties. They are not fluctuating, this we know from the perfect correlations. And so it seems to be the only possibility that we could, at least in principle, talk about what would happen if we were to do any of these measurements. But your question, of course, goes exactly in the right direction. This is something that we will have to re-examine. Only at this point, any reasonable person, I think, would say this all makes sense and there is no other choice. Good. So now let's go back in history, 70 years, 90 years actually. Let's go back and discuss the Einstein-Podolsky-Rosen paper. And that is a paper from 1935. It is so famous that there is this acronym EPR, after the authors Einstein-Podolsky and Rosen. And the question from which they started is the question that I also used to motivate this chapter, namely, is quantum mechanics the result of some underlying deeper theory? And the example for this, I already mentioned, it would be if you start from classical mechanics, particles moving under the action of mutual forces, then you can, in principle, go to statistical physics, having a gas of many such particles, getting the Boltzmann distribution. And from there, you can go to thermodynamics or hydrodynamics, which work on the macroscopic level. And so in that sense, if you were to start from hydrodynamics or thermodynamics, you wouldn't know where the equations come from, but you could trace your way back towards the microscopic level and to classical mechanics and individual particles interacting with forces. And this would give you some extra insight, for example, in why the laws of thermodynamics look like they look, or in hydrodynamics, you could maybe calculate the constants that otherwise just appear in these equations, like the viscosity and so on. Now, there is one problem if you wanted to look for such a deeper underlying theory, and that is the problem we already discussed when we discussed Heisenberg microscope or Copenhagen interpretation, and that is that there seems to be no trajectories. Yeah? And there seem to be no trajectories because you cannot measure position and momentum at the same time. In fact, if you analyze it, even with relatively simple quantum mechanics, you find that if the position measurement localizes your particle very much, then after this measurement, the wave function is so localized that it has a very large momentum spread. And so the momentum after this position measurement has become so uncertain that if you do now a momentum measurement, it will just show something random. And it is presumably not related to anything you would have found about the momentum before you did the position measurement. Yeah, so this is the fundamental problem if you start down this road of trying to find a deeper underlying theory. So you cannot even think of trajectories, it seems, or so at least Copenhagen wants us to believe, because x and p cannot be measured simultaneously. And again, this is because the measurement of say, x perturbs the momentum very strongly. Okay. So now, what was their trick? What was their new trick? They wanted to know both x and p. So they want to construct a situation where both x and p of a particle can be determined simultaneously and with certainty. Okay, that seems a contradiction. But if, and in a moment we will see their trick, what they are really doing. But in a moment, what would be the conclusion if you could construct a situation? That is the question. Now, quantum mechanics apparently never assigns definite values simultaneously to both position and momentum. We just said this. So either you have a wave function that has a large momentum spread or it has a large position spread, but it cannot be very well localized both in position and momentum. So since quantum mechanics never assigns definite values simultaneously to position and momentum at the same time, it seems not to describe these elements of reality, and therefore they would say in their language it is an incomplete theory. So if we can construct such a situation, then X and P could be called elements of reality because we can know both of them simultaneously, at least in principle. But quantum mechanics does not at the same time assign definite values to these elements of reality. So in some sense, then, quantum mechanics is incomplete because it does not talk about everything that could be in principle talked about. Okay, so this was their goal, to show that quantum mechanics is an incomplete theory and that presumably, therefore, there has to be an underlying deeper microscopic theory, maybe some theory that does talk about trajectories of quantum particles. And the goal would then be to find this more microscopic theory. Okay, there's still one question about our boxes, but maybe you can ask this question again in the chat channel, in the Google group, and so we can discuss this, because right now I wanted to go on here, if that's okay. Okay, so the question is, how do they do this? Because we just said that even Heisenberg's uncertainty relation doesn't allow X and P to be sharp at the same time. And we also know physically they cannot be measured simultaneously. If you really measure the position very precisely, you produce a large perturbation for the momentum. And we will maybe discuss this in some more detail later when we come to measurements in more detail. So how is that possible? They were very smart, as you might expect. And so their idea was to construct a situation where, first of all, you have two particles. Second, these two particles are very correlated. And they are correlated in such a way that, third, if you were to measure the position of one of them, you could immediately infer the position of the other one. But since you just infer it, and you don't actually measure the second position, you can still choose to measure something else, like the momentum of the second particle. So that's it in a nutshell, and we will now go through it. So the idea, the trick is to again build up correlations between this works now. We stopped, so to speak, at the most exciting moment, as is usual. So the sound was quantumly entangled, yes, maybe. So they wanted to produce two particles, but in a very smart wave function, where there's correlations, perfect correlations between the positions, for example. So you have a wave function, psi, of two particles. So you have two coordinates, x1 and x2. And then you say, oh, let me take this wave function to be a delta function that makes sure that x1 equals x2. Yeah? So this delta function enforces x1 equals x2. I write a proportional sign for the simple reason that this is a wave function that does not depend on the, it only depends on the distance between the particles. It does not depend on the center of mass coordinates, x1 plus x2 half. And as a consequence, right now it's not really normalizable. If you wanted to normalize it, you would have to write down a slightly more complicated wave function that is not extended infinitely over space. But these are details that don't really change the reasoning. So for the moment, let's just keep it like this. Now, this way of writing the wave function tells us that always when we measure things, x1 will turn out to be equal to x2. So if we do a measurement of x1 and x2, x1 will turn out to be equal to x2. This is how the wave function has been constructed. Now, the beauty of this particular wave function is that you can also switch to momentum space simply by doing a Fourier transform as usual, and then you will see something funny. So the delta function, as you hopefully maybe know, can be written in terms of a Fourier transform. So the idea is to take a Fourier transform over e to the I p times x1 minus x2. Now, this is still something that doesn't completely work. If p has the dimensions of a momentum, to get these things right, you should do divide by h bar and divide by 2 pi to get normalization. But these are details. So this is, at least at first, it's simply a mathematical identity. It's correct. But you can also interpret it in the following way. This is now a superposition of many states, each of which distinguished by a different value of the parameter p. So it's a superposition in the sense, instead of a sum, you have an integral, but okay, so it's an infinite superposition. And each of these states is this kind of plane wave. But you can also write this another way. You can say it's e to the ip times x1 times e to the minus ip times x2. Yeah. So the first one is a plane wave for the particle number 1, and the second is a plane wave for particle number 2. The first one has a definite momentum. Let's call it p1 equals plus p. And the second part has a definite momentum p2 equals minus p. Yeah, so this is the meaning of this particular wave function. Now, the funny thing is, immediately we again get perfect correlations. Namely, now if you were to measure the two momenta, then you would figure out, aha, p1 equals minus p2. Yeah, that's the meaning of these two statements. P1 is plus p, p2 equals minus p. Regardless of which particular value of p you measure, it's always true that p1 equals minus p2. And so magically, you have constructed a wave function. Let's summarize this again, and then it's enough for today. You have constructed a wave function where if you measure the positions at both sides, you always get x1 equals x2 in any measurement of positions. Whereas if you choose to measure the momenta on both sides, you get p1 equals minus p2 in any measurement of the two momenta. Yeah. So if you're not so familiar with switching between position and momentum space or decomposing a wave function into such a superposition, maybe you have to think a bit about it. But essentially, that's the idea. They have constructed a two-particle wave function with perfect correlations between the positions in a position measurement and perfect correlations between the momenta in a momentum measurement. And so this is where we will leave off today and where we'll continue the next time. But the idea, maybe I can already preview now. The idea is that, as I said before, you can choose to measure x1 and then you infer the value of x2. It's simply equal to x1, and you are certain of that because whenever you would now measure x2, you would find that value. But instead of actually
performing the measurement on x2 and confirming that there is this identity, you say, well, why should I waste my precious measurement on something that I already know? I know that x2 equals x1. So on particle 2, I'm smart, and I'm actually measuring the momentum, p2. And so then I know everything about particle 2, both x2 and p2. x2 by inferring it from x1, and p2 by direct measurement. And so we will discuss next time why, at least at first sight, you can conclude that this should be possible, and that this then means both x and p are in some way already present in these particles, even though maybe you cannot measure them simultaneously. So now there are questions still. Yes, there are no trajectories in the Copenhagen interpretation, but if we take some other interpretation, there can be trajectories. Yes, thank you. This is something we will come back to later. And that's, of course, historically came much later. And Einstein-Podolsky-Rosen didn't know about this, but they were hoping for something like this. Maybe even without having to deal with the wave function in addition. Why should the two-particle wave function be a delta function? This is not a very general wave function. Yeah, that's true. It's not very general, but that was not their purpose. They wanted to construct a particular scenario with a particular wave function, which is just set up in the right way to give them the perfect correlations. Of course, if you take arbitrary wave functions, you cannot play the same trick, but that they don't need for their logic. Their logic is just to show in a particular situation that you can know both the position and the momentum at the same time, and that therefore you should ascribe to them some reality, even independent of measurement, and that therefore, since quantum mechanics does not talk about them at the same time, quantum mechanics must be considered an incomplete theory. So for them, for their purpose, it's good enough to show this for a single wave function. Now, if we measure the position here, doesn't it become a classical particle? Well, it doesn't become really a classical particle, but it becomes very localized. Maybe this is what you mean. And at least in terms of the position, I could then say it's like a point particle that has been localized at some spot. In that sense, it's similar to a classical particle. Okay. Good, I hope I answered all the questions. I'm aware of this little bug on the website. I will put up the slides, link to them. And maybe that's it for today.